Hi everyone, I'm Lorenzo from NVIDIA, and today I'm going to briefly discuss a little bit how you can embed a domain-specific language in C or C++ using Polygeist. This is a work that I have in collaboration with William Moses at the University of Illinois, Urbana-Champaign. So before going into the details, let me first give you a little bit of motivation on why we want to do that. So I don't need to convince you that today programming hardware is getting more complex. Hardware itself is getting more heterogeneous and more high-level. And the typical response from the software community to this increase of abstraction in the hardware stack has also been an increase in abstraction in your software. And to achieve that, what you can do is to essentially developing a domain-specific language and a domain-specific compiler. However, these tools do not come from free. Usually, you have compatibility issue also, and composability issue between those, and they're really, really hard to integrate into existing large code base. And the main motivation is usually this tool are basically monolithical piece of software. And this means that, and this actually is due to the tight integration that exists between the language and the software. So essentially with this project, what we aim at achieving is to design a set of mechanisms that allow us to bring a domain-specific language to existing C or C++ project in an easier way. So effectively, what we want to do is to tear down the barrier that exists between this domain-specific word and the general-purpose one. We do that by essentially reusing novel compiler technology. So we build on top of MLIR, and specifically what we did here is to add a mechanism, an extension mechanism to Polygeist, which essentially allow you to bring a domain-specific language and compiler as a set of plugin. And we call this extension mechanism syntax plugin. So for those of you that do not know what Polygeist is a C or C++ front end for MLIR, among many other things. And essentially what it allows you to do is to take an arbitrary piece of C or C++ and translate to the corresponding IR that may belong to different dialects within the MLIR framework. So this slide shows a simple example. So you have a 2D nest loop here. And on the left and on the right, you have the corresponding IR. And you see that the beauty of Polygeist is essentially that allow you to preserve the rich semantics of your language. So in this case, a 4 in C corresponds to an SCF4 in the SCF, the standard control flow dialect in MLIR. And also you can preserve the dimensionality. So in this case, you have a 2D array, and you see also that your memory are 2D. Essentially, Polygeist achieved this by essentially relying on Clang. So you build the Clang IST, and then you scan the IST, and for each IST node, emit the proper IR. So let me tell you a little bit what we have in mind here and how actually is the plan to bring this domain-specific language and their transformation in a general-purpose flow. So I think we need to basically work on 3 main areas. So the first one is that we want to bring custom syntax. So for instance, if you're some expert in the linear algebra domain, you may want to write your application using a custom syntax. So you don't want, or you're not interested in writing C or C++. The second way is that we also need to give you a mechanism to bring your own knowledge into the compiler. And this can happen essentially in 2 ways. One, as a form of rewriting rule, or it can happen also as a form of operation. So you may, for instance, be able to dynamically inject an operation in the compiler and give semantics to the operation itself. So for the purpose of this talk, I will just focus on syntax and rewriting rule. In Polygeist, we already have some experimentation with operation itself. So for instance, you can mark a function with pragma, and then this function will get lowered to a custom op in MLIR, but it's not dynamically. So we need to basically pick a dialect and lower to it. Okay, so let me give a little bit of an idea about the syntax. So essentially for the syntax, what we did is that we re-implement an idea that has been proposed a few years ago by Finkel et al., which essentially consists of a Clang extension that allow you to fundamentally alter the syntax that is parsed by Clang parser. Essentially what this means is that you can now go and mix C code with DSL code. As long as some parsing rules are essentially respected. So for instance, the limiter need to be balanced. And this is a simple example of that. So you see that now the C function has been marked with attribute, Clang syntax, and then within brackets you have the name of the plugin, which essentially is a simple shared library that will get loaded by Polygeist and will tell to Polygeist how you should interpret the body of the function. So the arguments are simple C code, but you see that now the body is a DSL code. So for this specific case, we use tensor comprehension, which is a DSL language to express linear algebra computation. So practically speaking, this works as a two-step approach. So during the parsing phase, what happens is that Clang will parse the body of the function. So we then take the parsed tokens, store them away. And in the next phase, so basically when Polygeist starts scanning the IST and build the IR construct, what we do is that we retrieve the parsed token, hand off to the plugin, and the plugin will then be responsible to emit the function body. So as I said before, the plugin is a simple shared library and consists of a parser plus an IR emitter, so it's fairly simple. And here in this slide, basically on the left, you have the IST that is generated by the plugin, which essentially represents a single transpose operation. While on the right, you have the emitted IR. So in this case, the transpose operation is lowered to a linear generic, which is a high-level operation that belongs to the linear algebra dialect. Notice that basically a function boundary Polygeist will handle the IR emission, and then we'll pass, for instance, a symbol table to the plugin so that the plugin can understand what are these arguments and stuff like that. And also another things that we do here is that, for instance, we upcast from memref to tensor because we want to reuse some optimization that are available in Linux. Okay, so now we brought the syntax. So let's see how we can bring optimization. So imagine that you're writing your library. So now you have a kind of nice way to write your transpose kernel, but now you want to inject an optimization there. So to inject optimization, what we provide to you is what we call tactics. Essentially, tactics represent how you can rewriting a rule, and the pattern tell you essentially what you want to match, while the replacement tell you how you want to replace what has been matched. And in this case, the tactic is fairly simple, so it's detect a transpose of a transpose and replace it with a single copy operation. Practically speaking, these tactics get lowered to the transform dialect, specifically to some matchers that are available in the linear dialect that allow you to reason a little bit about the property of the operation, like the structure as well as the access pattern. So specifically, for instance, assuming that you want to detect a transpose, what you want to make sure is that your generic is a 2D. Then you want to make sure that all your dimensions are parallel. And you also want to make sure that the input and output is consistent with what would you expect for a transpose, so one input, one output. And then you finally look into the access pattern, so the input must be an identity and the output must be a projected permutation. Finally, you also look at the body and make sure that the body doesn't do anything fancy, so in this case it should just be a pass-through op. So once we have match, what we can do is now we can go and replace. So for this, again, we use transform dialect. Specifically, we use the structure replace op, which allow you to take an input, a set of SSA operand that are the new operand for the operation that you're going to inject. And the payload of the operation is the replacement. So the replacement in this case is yet another generic, but is a copy rather than a transpose. And I mean, all of this is actually generated from this statics, essentially. Okay, so all in all, I give you a little bit of a brief idea of what we're building here. So essentially, what we aim at achieving is to try to mix C code with DSL code, and I think it's quite a good time because we have novel compiler technology that allows us to do that. And essentially, the big goal that we want to do is to try to tear down this barrier that exists between these two worlds. Feel free to get in touch with us, you can either send us an email or we can chat also here. Thank you.
Thank you, Lorenzo.